Hello, in this video we'll discuss section 6.1, analyzing antiderivatives graphically and numerically. In particular, we'll look at an example where we analyze an antiderivative graphically. But first, what is an antiderivative? Suppose we start with the function x squared. By now you can all take the derivative. We know the derivative is 2x. But what if we want to go in the reverse direction? Start with this function 2x, which I'll denote by little f of x. What is something whose derivative is this? So I'm looking for the something that should go in this box. Its derivative should be 2x. Well, that something is x squared. We'll denote it by big F of x. And we'll say that big F of x is an antiderivative of little f of x, since big F prime of x equals little f of x. In the next video, we'll see that we actually get an entire family of antiderivatives for 2x, but for now, it's enough to know that x squared is something whose derivative is 2x. Let's look at an example. We're going to be given the graph of a function, little g of t, and we want to sketch a graph of an antiderivative, big G of t, of little g of t, satisfying g of 0 equals 5. Since big G of t is an antiderivative of little g, we have big G prime of t equals little g. We're also asked to label each critical point of big G of t with its coordinates. So again, here is the graph of little g. We want to sketch a graph of an antiderivative of this. So let's start by finding the critical points of big G of t. And if you think back to the definition of critical point, it's a point for which the derivative is 0 or does not exist. This means we need to find points for which big G prime of t is 0 or big G prime of t does not exist. Looking at the graph, there are no places where the derivative does not exist, but we do have a few places where the derivative is 0. It's 0 at here, t equals 0, t equals 2, 4, and 5. Now we can also decide where this function big G is increasing and decreasing. We know big G will be increasing if its derivative is positive. So let's look for places where the derivative, big G prime of t, is positive. Well, from 0 to 2 and 4 to 5. The graph lies above the t-axis. So on these intervals, big G is increasing. And we know big G will be decreasing when its derivative is negative. That happens on this interval from 2 to 4. We'd also like to be able to decide where big G is concave up and where it's concave down. Now we know big G will be concave up when its second derivative is positive. Well, what is big G double prime? If we go back to this label here, big G prime is little g. So to find big G double prime, I need to take the derivative of this. In other words, we have little g prime of t. So we're really trying to decide where is little g prime of t positive. And of course, that will happen when little g is increasing. So I'm really trying to find the intervals where little g is increasing. And it looks like that happens from 0 to roughly 0.7 and 3 to 4.5. So those are the places where big G is concave up. And now to decide where big G is concave down, we need big G double prime to be negative. In other words, we need little g prime to be negative. So we're looking for places where little g is decreasing. And this happens on the interval roughly 0.7 to 3 and 4.5 to 5. Now we can determine the values of big G at these critical points using the fundamental theorem of calculus. So, for example, by the fundamental theorem, the definite integral from 0 to 2 of g prime of t is equal to the total change in g on this interval 0 to 2. In other words, this definite integral is equal to g of 2 minus g of 0. And so I'll get g of 2 by itself by adding g of 0 to both sides of the equation, and we have this. G of 0 was given to be 5, and now the value of the definite integral from 0 to 2 is the signed area. We're told the area of this region is 16. Because it lies above the t-axis, it's positive, and g of 2 is 21. Similarly, g of 4 would look like this. The definite integral from 2 to 4 in this case is -8 because this region lies below the t-axis. So we end up with 13 for g of 4. And finally, g of 5 looks like this. The value of the definite integral from 4 to 5 would be +2, since that piece lies above the t-axis. Putting all of this information together, we're able to produce a rough sketch of a possible graph of big G of t. Notice I've labeled the critical points, which occur at t equals 0, 2, 4, and 5. And we've also used the information about where big G is increasing and decreasing, as well as concave up and concave down. So this is a possible sketch of the graph of big G of t. We'll stop there for now.